12.1 Introduction. Let us focus on some of the statements below. As there is rise in temperature, there is increase in sale of ice creams. As there is increase in occupational stress experienced by employees, their performance may go down. Sale of air purifiers can be linked to the increase in pollution. In our day-to-day life, we may experience such associations, that is, when one aspect increases or decreases, another aspect also increases or decreases, or when one aspect increases, the other decreases, and vice versa. To take more examples, a researcher may be interested in studying whether there exists a relationship between self-esteem and achievement motivation of asterisks. Or a researcher may be interested in finding out if there exists any relationship between psychological well-being and job satisfaction of employees in an organization. In such cases, correlation will help the researcher study the relationship and also understand its direction and magnitude. In research, studying relationship between two or more variables could be an important objective, and this can be studied with the help of correlation. In the present unit, we will focus on the concept of correlation, its direction and magnitude. The properties, uses and limitations of correlation will also be covered besides other methods of correlation. 12.2 Concept of correlation, direction and magnitude of correlation. Let us take another example to understand the concept of correlation. A research was carried out by a researcher on relationship between years of experience and monthly income earned by junior managers in an organization, hypothetical data.
This is that hypothetical data, that is 12.1 years of experience and monthly income of junior managers.
What do you understand? You may notice that as the years of experience is increasing, the monthly income earned by the junior managers is also increasing. Thus, it can be inferred that in case of these junior managers, there is a positive relationship between the years of experience and the monthly income. Let us take another example. An experimenter was carrying out a study on relationship between hours of practice in a certain task and number of errors committed by the participants. The data obtained from the same is given as follows.
Table 12.2 hours of practice in certain task and number of errors.
Follows. Table 12.2 hours of practice in certain task and number of errors per this data, it can be seen that as the hours of practice is increasing, the number of errors committed by the participants is decreasing. Thus, it can be said that there is a negative relationship between hours of practice and number of errors committed. With the above examples, you must have developed some idea about what is correlation. Let us now look at the concept of correlation and also focus on its direction and magnitude. Correlations can be used to study relationship between two or more variables. It is a measure of association between two or more variables, and this relationship is determined not only in terms of direction, whether negative or positive, but also in terms of its magnitude, whether high or low. However, it will not provide information about any causal relationship between the variables. Sir Francis Galton's contribution to development of correlation is noteworthy. He carried out studies on individual differences and also studies on the influence of heredity. He studied the association between the height of parents and that of their children with the help of bivariate distribution, that studies relationship between two variables, and found that the parents who are tall have children who are also tall. Viraragavan and Shigavakar, 2016. Further, in 1986, Carl Pearson put forth mathematical procedure for correlation. Correlation can be categorized into linear and nonlinear correlation. These are discussed as follows. Linear correlation. Linear correlation is denoted by a single straight line in a graph that denotes linear relationship between given two variables. Such a graph indicates whether increase in one variable leads to increase in another variable and vice versa, or decrease in one variable leads to increase in another variable and vice versa. For example, if the scores on emotional intelligence increase or decrease, the scores on self-esteem also increase or decrease. Linear relationship is graphically represented in figure 12.1. Nonlinear correlation. As opposed to linear relationship, in nonlinear relationship, the relationship between two given variables is not denoted by a straight line. Thus, the relationship is curvilinear as denoted in figure 12.2. 12.2.1 Direction and magnitude of correlation. With the help of examples that we discussed at the start of this section, it must be clear that correlation can be either positive or negative, though there could also be no relationship between the given two variables. This can be described as direction of correlation. Let us now discuss these in detail. Positive correlation. Positive correlation denotes that increase in one variable leads to increase in another variable and decrease in one variable leads to decrease in another variable. For example, if the scores on emotional intelligence obtained by adolescents increase, then the scores obtained by them on achievement motivation will also increase, or if the scores on emotional intelligence obtained by adolescents decrease, then the scores obtained by them on achievement motivation will also decrease. Positive correlation indicates that both the variables are moving in same direction. Refer to point 3 as a scatter diagram denoting positive relationship between two variables. A and B scatter diagram can be effectively used to present a bivariate distribution that denotes relationship between the two variables. Negative correlation. Negative correlation denotes that increase in one variable leads to decrease in another variable, or decrease in one variable leads to increase in another variable. For example, if the scores on occupational stress obtained by employees increase, then the scores obtained by them on work motivation will decrease, or if the scores on occupational stress obtained by employees decrease, then the scores obtained by them on work motivation will increase. In this case, the two variables are not moving in same direction. Figure 6.4 is a diagrammatic representation of negative correlation. Correlation, no correlation, or zero correlation. It may so happen that there is no relationship between the two variables. In such a case, the correlation will be zero. This will be further clear as we discuss the magnitude of correlation. Thus, in this case, the relationship is neither positive or negative. There are such variables where there might be no relationship. For example, there may be no correlationship between height of persons and years of their work experience, or there may exist no relationship between weight of persons and attitude towards environment. No correlation is represented in form of scatter diagram in figure 12.5. Zero correlation. Besides the direction of the correlation, it is also significant to understand the magnitude or strength of the correlation. Magnitude is denoted by the degree of linearity of the correlationship. Correlationship between any two variables is coefficient of correlation that is quantitatively represented. And the range for a coefficient of correlation is between -1 to +1. Thus, coefficient of correlation can be obtained as 0.28 or -0.09 or 0.75 and so on. The number will lie between -1 to +1, and the plus and signs denote the direction of correlation, whether it is positive or negative. The obtained coefficient of correlation can be interpreted with the help of the table 6.3 given as follows. Mongal, 2002, page 105.
Table 12.3 इंटरप्रिटेशन ऑफ कोएफिशिएंट ऑफ कोरिलेशन, इसमें डेटा दिया गया है, आप लोग देख सकते हो. While interpreting coefficient of correlation, it is important to keep in mind the direction based on the positive and negative signs. 12.2.2 scatter diagram. One way in which relationship between the two variables can be denoted is by using scatter diagram. Scatter diagram is also called as scatter plot or scattergram. It is drawn by plotting the two variables in same graph. That is variable A on y-axis and variable B on x-axis. Okay, ये figure 12.3 और 12.4 और 12.5 में दिखाया गया है. Table 12.4 is also showing us the marks of psychology and sociology of Peter, Sarika, Kamaldeep, Sarman and Arvind. As an example, we want to study the relationship between marks obtained by 5 students in psychology and sociology in class test. The data is given in the table above, which I already told. The जो स्केटर डायग्राम जो बना हुआ है आप लोग स्क्रीन पे देख सकते हो. ठीक है, ये स्केटर डायग्राम आपने अगर आप देखोगे तो आपको पता चलेगा कि रिलेशनशिप कोरिलेशन कैसा, कोएफिशिएंट ऑफ कोरिलेशन कैसा है. ठीक है,
As can be seen from the graph, there is a linear relationship between the marks obtained in psychology and marks obtained in sociology. Coefficient of correlation can be computed with the help of Pearson's product moment correlation and Spearman's rank order correlation that will be discussed in the next units of correlation. As the concept of correlation is now clear, we will discuss about its properties, uses and limitations. 12.3.1 Properties of correlation. 1. The variables used in correlation are quantitative in nature. 2. The value of coefficient of correlation will range from -1 to +1n. Correlation can be positive or negative, or there can also be zero correlation. 3. As we have discussed before, correlation will provide information about relationship between the variables, but it will not denote whether a cause and effect relationship exists between the variables. For example, we may obtain a positive correlation between organizational culture and job satisfaction of employees, but correlation will not denote if there is a cause and effect relationship between these two variables. 4. It is not possible to make any predictions based on correlation. For example, there may be positive correlation between rise in temperature and sale of ice cream or cold drinks, but the sale of ice cream or cold drinks cannot be predicted based on the temperature with the help of correlation. 5. Even if variables randomly vary, correlation can be used. 6. Sampling errors can have an effect on correlation. 12.3.2 Uses of correlation. Correlation can be used for varied purposes that have been discussed as follows. Mohanty and Misra, 2016. 1. Validity and reliability. Validity and reliability are important aspects of psychological testing, and correlation can be used to obtain validity and statistical methods. 220. Reliability of a psychological test. Validity is whether a test is measuring what it is supposed to measure, and reliability provides information about consistency of a test. 2. Verification of theory. Correlation can also be used to verify or test certain theories by denoting whether relationship exists between the variables. For example, if a theory states that there is a relationship between parenting style and resilience, the same can be tested by computing correlation for the two variables. 3. Putting variables in groups. Variables that show positive correlation with each other can be grouped together, and variables that show negative correlation can be grouped separately based on the coefficient of correlation obtained. 4. Computation of further statistical analysis. Based on the results obtained after computing correlation, various statistical techniques can be used, like regression. Further, correlation is also used for multivariate statistical analysis, especially for techniques like multivariate analysis of variance, MANOVA, multivariate analysis of covariance, Mankova, discriminant analysis, factor analysis, and so on. Mohanty and Misra, 2016. 5. Based on correlation, one can decide whether or not to determine prediction. By computing correlation, it is not possible to predict one variable based on another variable, but based on the information that two or more variables are significantly related to each other. Further statistical techniques can be used to make predictions. For example, if we obtain a positive correlation between family environment and adjustment of children, then further statistical techniques can be employed to find if adjustment of children can be predicted based on family environment. 12.3.3 Limitations of correlation. Some of the limitations of correlation have been discussed as follows. 1. As was stated earlier, correlation will not provide any information about cause and effect relationship or causation. 2. The coefficient of correlation, mainly Pearson's product moment. Correlation and Spearman's rank order correlation are suitable when there is a linear relationship between the variables. 3. With regard to distributions that are discontinuous, the coefficient of correlation obtained may be overestimated or higher. 4. Sample variations can have an effect on correlation, as is also true with other statistical techniques. 5. In case of pooled sample, the correlation will be determined by relative position of the scores in x and y dimensions or variables. Correlation. An introduction. Point 4. Other methods of correlation. There are various other methods of correlation as well, that will be discussed in the present section of this unit. 1. Partial correlation. In partial correlation, the relationship between two variables is studied by controlling the influence of a third variable. For example, if we are studying the relationship between emotional intelligence and self-concept of adolescence, we may partial out or control the third variable, for instance, family environment. 2. Part correlation. This is also called as semi-partial correlation. This is in a way similar to partial correlation, but here is the correlationship between two variables is studied. The influence of third variable on one of the variables is controlled. Taking the example discussed under partial correlation, the influence of family environment only on emotional intelligence is controlled and not on self-concept. 3. Multiple correlation. In multiple correlation, one variable is correlated with many other variables. For example, self-concept will be correlated with various other variables like emotional intelligence, achievement motivation, quality of life, and so on. 4. Biserial correlation. In biserial correlation, the relationship is measured between a continuous variable and an artificially dichotomous variable. A dichotomous variable is a variable that can be categorized into two. For example, socioeconomic status could be high and low. An example of biserial correlation would be relationship between achievement motivation and high and low emotional intelligence. Here, achievement motivation is a continuous variable and emotional intelligence is a variable that is artificially dichotomous. 5. Point biserial correlation. In point biserial correlation, the relationship is measured between a continuous variable and a naturally dichotomous variable. Examples of naturally dichotomous variables are gender, male and female, religion, Hindu and Muslim, and so on. For example, point biserial correlation can be used when we want to find out relationship between work motivation, continuous variable, and gender, naturally dichotomous variable. 6. Tetratoric correlation. When both the variables are artificially dichotomous, then tetratoric correlation can be computed to study the relationship between the two variables. For example, tetratoric. Statistical methods. 222. Correlation can be used when we want to study the relationship between variables, emotional intelligence, that is categorized into high and low, and adjustment, that is categorized into well-adjusted and maladjusted. 7. Phi coefficient. This is similar to tetratoric correlation, but is used when both the variables are naturally dichotomous. For example, if we want to find relationship between gender, that is categorized as male and female in response to a statement in terms of agree and disagree, then Phi coefficient can be computed. 12.5 Let us sum up. In the present unit, we mainly discussed about the concept of correlation. Correlation can be used to study relationship between two or more variables. It is a measure of association between two or more variables, and this relationship is determined not only in terms of direction, whether negative or positive, but also in terms of its magnitude, whether high or low. Correlation can be categorized into linear and nonlinear correlation, and these were discussed in the present unit with the help of figures. The concept of scatter diagram was also briefly discussed in this unit. Scatter diagram is also called as scatter plot or scattergram and is drawn by plotting the two variables in same graph, that is, variable A on y-axis and variable B on x-axis. Further in the unit, we also discussed about the properties, uses and limitations of correlation that are relevant, so as to know when exactly to use correlation. In the last section of this unit, we focused on the other methods of correlation, including partial correlation, part correlation, multiple correlation, biserial correlation, point biserial correlation, tetratoric correlation, and Phi coefficient. In the next unit, we will learn how to compute coefficient of correlation with the help of Pearson's product moment correlation and Spearman's rank order correlation. It is a measure of association between two or more variables, and this relationship is determined not only in terms of direction, whether negative or positive, but also in terms of its magnitude, whether high or low. Linear correlation. Linear correlation is denoted by a single straight line in a graph that denotes linear relationship between given two variables. Multiple correlation. In multiple correlation, one variable is correlated with many other variables. Nonlinear correlation. Here the relationship is not denoted by a straight line, but it is curvilinear. Negative correlation. The negative correlation denotes that increase in one variable leads to decrease in another variable, or decrease in one variable leads to increase in another variable. No correlation or zero correlation. When there is no relationship between the two variables, the correlation will be zero. Thus in this case the relationship is neither positive or negative. Part correlation. This is also called as semi-partial correlation. Here is the relationship between two variables is studied. The influence of third variable on one of the variables is controlled. Partial correlation. In partial correlation, the relationship between two variables is studied by controlling the influence of a third variable. Point biserial correlation. In point biserial correlation, the relationship is measured between a continuous variable and a naturally dichotomous variable. Phi coefficient. Phi coefficient is used when both the variables are naturally dichotomous. Positive correlation. The positive correlation denotes that increase in one variable leads to increase in another variable, and decrease in one variable leads to decrease in another variable. Scatter diagram. Scatter diagram is drawn by plotting the two variables in same graph, that is variable A on y-axis and variable B on x-axis. Tetratoric correlation. When both the variables are artificially dichotomous, then tetratoric correlation can be computed to study the relationship between the two variables.
So far the length of the unit 12 was only 17 to 18 minutes, and I would also like to join unit 13 to the same video, so that you will get both unit 12 and 13 in a single video. Let's continue then.
Unit 13 Computation of Coefficient of Correlation. 13.1 Introduction. In the previous unit, we discussed about the basics of correlation. We discussed that correlation indicates relationship between two or more variables. This correlation can be interpreted in terms of direction and magnitude. Thus, a relationship between given two variables can be positive, negative, or there could be no correlation. Further, the correlation may range between +1 to -1. In the present unit, we will learn about the computation of correlation with the help of Pearson's product moment correlation and Spearman's rank order correlation. One way in which these two methods can be distinguished is that Pearson's product moment correlation can be categorized under parametric statistics, and the Spearman's rank order correlation falls under nonparametric statistics. To distinguish between parametric and nonparametric statistics, the following table, Table 13.1, can be referred to, * Professor Shu has Nonparametric statistics, parametric, nonparametric. The assumed distribution is normal. The assumed distribution may not be normal. It can be any distribution. The variance is homogeneous. The variance could be heterogeneous, or no assumption is made with regard to the variance. The scales of measurement used are interval or ratio. The scales of measurement used are nominal or ordinal. The relationship between the data needs to be independent. There is no assumption with regard to the independence of relationship between the data. Mean is the measure of central tendency that is used here. Median is the measure of central tendency that is used here. It is more complex to compute when compared to the non-parametric techniques. It is simple to calculate. Can get affected by outliers. Is comparatively less affected by outliers. In the next section, moment correlation. 13.2 Pearson's product moment correlation. Pearson's product moment correlation is one of the methods to compute coefficient of correlation. This is mainly used when the assumptions of parametric statistics are met. This method is named after Carl Pearson, who invented this method. It is denoted by R. 13.2.1 Assumptions of Pearson's product moment correlation. The assumptions of Pearson's product moment correlation are as follows. 1. The variables used to compute R are continuous in nature and the scales of measurement are interval and ratio. 2. The distribution of the variables in this method is unimodal and it is close to symmetrical. The distribution need not be normal. 3. The pairs of scores involved are independent in nature and are in no way connected with other. 4. There is a linear relationship between the two variables. A scattergram, thus drawn with the help of scores in the two variables, will denote a straight line. 5. R is mainly used to ascertain the sign and size of the correlation that can be positive, negative or zero correlation and will range between -1 to +1. Computation of coefficient of correlation. 229. 13.2.2 Uses of Pearson's product moment correlation. 1. It helps in determining the relationship between two variables. Quantitatively. With quantification, it is possible for us to compare. 2. Based on R, regression equation can be computed. Thus, after computing R, it is possible to compute regression and determine whether one variable can be predicted based on another variable. 3. R can be used in computation of reliability and validity of psychological tests. 4. It will also assist in computation of factor analysis. 13.2.3 Computation of Pearson's product moment correlation. There are two main methods that we will discuss for computing Pearson's product moment correlation. They are discussed as follows. Method 1. The formula for the first method is given below. Rxy equals sigma xy n sigma x sigma y, where R equals correlation x equals deviation of any score of x from the mean of xy equals deviation of any score of y from the mean of y. Sigma xy equals indicates the sum of all the products of deviation, that is, each x deviation is multiplied by its corresponding y deviation. Sigma x equals standard deviation of scores in x. Sigma y equals standard deviation of scores in y. N equals total number of participants, frequencies. The formula can be simplified as follows. Sigma x equals square root sigma x2, n. Sigma y equals square root sigma y2, and thus, by substituting the values for sigma x and sigma y, the following is obtained. R equals sigma xy, n square root sigma x2, n square root sigma y2, n equals sigma xy, square root sigma x2 sigma y2. Let us understand this method and steps involved in it. With the help of an example, a researcher wanted to study the relationship between data 1, x, and data 2, y. The data is given below. Statistical methods 2. 230. Participants 1. Data 1 totaled separately. Thus, sigma x and sigma y is obtained as can be seen above in the second and third column. N is also noted and in this case it is 10. Step 2. Mean is now computed for the data 1, x, and 2, y, as follows. Mean for scores on x equals 30 tenths equals 3. Mean for scores on y equals 40 tenths equals 4. Step 3. In the third step, deviation is computed for each score of x from its mean, that is, 3 in the case of this example. In a similar manner, deviation is computed for each score of y from its mean, that is, 4. These are entered in the column 4 and 5 above under headings x and y, respectively. Step 4. The values thus entered under x and y are multiplied and entered in column 6, and then they are also squared and entered under column 7 and 8 with headings x2 and y2. Further, the scores under each of these columns are totaled to obtain sigma xy, sigma x2 and sigma y2. Step 5. Use the formula to compute R. R equals sigma xy, square root sigma x2 sigma y2. Equals 8, square root 10 times 8 equals 8, square root 80 equals 8/8. 94 equals 0.89. Thus, the coefficient of correlation obtained for the above data is 0.89, denoting that there is a positive and high relationship between the two data sets x and y.
मेथड 2 जो है वो आप अपने हिसाब से अपनी टेक्स्ट बुक में देख लीजिएगा, क्योंकि ये प्रॉब्लम्स जो है वो उसको खुद से ही सॉल्व करना पड़ता है। और टेक्स्ट बुक और नोटबुक को लेके, रफ बुक जो भी हो आपके पास, उसको लेके बैठ जाइए और सॉल्व कर दीजिए। यू विल हैव टू टेक लिटिल टाइम फॉर दैट। Okay, we will directly go for the Spearman's rank order correlation.
18.3 Spearman's rank order correlation. Another method to compute coefficient of correlation is Spearman's rank order correlation, also known as Spearman's row. This method is used when the assumptions of parametric statistics are not met. The method is named after Charles Spearman, who is known for his significant work on factor analysis and theory of intelligence besides Spearman's rank order correlation. 13.3.1 Assumptions for Spearman's rank order correlation. The assumptions of Spearman's rank order correlation are as follows. 1. The variables are measured in terms of ordinal scale. 2. The relationship between the two variables is linear in nature. 3. The observations are independent in nature, thus denoting that the sample needs to be randomly selected. 4. The pairs of scores are independent in nature and are in no way connected with other pairs. 13.3.2 Uses of Spearman's rank order correlation. 1. It is used when the data is measured with the help of ordinal scale. 2. It is especially useful when the sample size is small, that is, less than 25. 30. Mohanty and Misra, 2016. 3. Many a times it is not possible to measure traits directly. Thus, they are measured in terms of ranks. Spearman's rank order correlation involves separately ranking the scores in the two data, followed by computation of correlationship between them. Computation. 4. It can be used to study the degree of relationship between two variables that are monotonic. A relationship is termed as monotonic when the variables display consistent but one-directional relationship. 13.3.3 Computation of Spearman's rank correlation. There are two main methods that we will discuss for computing Spearman's rank order correlation, one without tied ranks and one with tied ranks. They are discussed as follows. Method 1. With
स्पीयरमैन रैंक ऑर्डर कोरिलेशन भी आपको ही अपने ही टेबल पे ही अपने ही किताब और टेक्स्ट बुक लेके सॉल्व करना है, क्योंकि ये जो प्रॉब्लम्स जो होते हैं वो खुद से ही किए तो अच्छे रहेंगे. आपको हेल्प हम करेंगे अगले वीडियो में. ये प्रॉब्लम हम खुद लेके सॉल्व करने का वीडियो भी बना रहे हैं, लेकिन रीड आउट में आपको ये पॉसिबल नहीं है. सो वी विल मेक एन अनदर स्पेशल वीडियोस फॉर द प्रॉब्लम्स दैट वी वांट टू सॉल्व. ओके, सो लेट अस सी दैट summing up of 13th unit.
13.4 Let us sum up. In the present unit, we mainly discussed about the two methods of computing coefficient of correlation. The first method is Pearson's product moment correlation and the other is Spearman's rank order correlation. Pearson's product moment correlation is one of the methods to compute coefficient of correlation. This is mainly used when the assumptions of parametric statistics. Statistical methods 236 are met. This method is named after Carl Pearson, who invented this method. It is denoted by R. Spearman's rank order correlation is used when the assumptions of parametric statistics are not met. The method is named after Charles Spearman, who is known for his significant work on factor analysis and theory of intelligence. The assumptions and uses of these methods were also discussed. The formula and computation for the two methods were discussed with the help of examples.
We will move on to Unit 14, Normal Probability Distribution.
Unit 14, Normal Probability Distribution. Point 1 Introduction. Let us understand the main concept of this unit, that is, normal probability curve with an example. Suppose we take variables like height or weight or psychological variables like intelligence or emotional intelligence and we asterisk Dr. Smita Gupta. Measure the same across a large population. We are likely to obtain a graph which will indicate that the maximum scores lie in the middle of the distribution and lower scores at the extreme. With regard to height, for example, there will be more persons with average height and few persons who are taller or shorter compared to the average. And when this data is plotted on a graph, we will get a normal curve as can be seen in figure 14.1. In the previous units, we discussed about the concept of statistics, data organization and graphical representation, measures of central tendency and variability, and we also discussed about correlation and its computation. In the present unit, you will be introduced to the concept of probability, normal probability curve and other related aspects. 14.2 Concept of probability. The term probability refers to chance or likelihood. For example, if you say that it will probably be hot tomorrow, or probably the teacher might not come tomorrow, the sentences reveal that there are chances for the events to occur tomorrow, but there is no certainty. This means that the events mentioned in the above examples are not certain to happen. Now, a question that might bother you is, what is research and statistics to do with probability? The probability of an event to occur due to certain reason helps the researchers to formulate hypotheses to continue with research and experiments. It serves as a baseline for the researchers to start as well as conclude their research. It is relevant in science and investigation and is also important in finance, gambling, artificial intelligence, mathematics and game theory. Researchers can draw conclusions on basis of probabilities. In simple terms, probability refers to the chance, possibility or likelihood of an event to occur. In statistics, the term probability refers to the expected frequency, chance of occurrence of an event among all possible similar events. The expected frequency of the occurrence of the event is based on knowledge or information about the conditions determining the occurrence of the event or phenomena. For example, if you toss a coin in air, there is an equal chance for head or tail to appear. Thus, the probability that head or tail will appear, when a coin is tossed in air, is 1/2 to appear. Similarly, a die, singular of dice, has 6 sides with dots ranging from 1 to 6. The probability of a die to show any of its side is 1/6. The probability is denoted in form of ratio in statistical terms, wherein a probability ratio is denoted as probability ratio equals desired outcome, S, or events total number of outcomes. Or events to make it more clear, the probability ratio of any side of the coin to occur. After each toss will be equals 1, either head or tail. 2. Total number of sides of coin. And the probability ratio of any side of the dice to fall is equals 1, any one side of the 6 sides. 6. Total number of sides of dice. A probability ratio always ranges between the limit of 0.00, impossibility of occurrence, to 1.00, certainty of occurrence. We can say that the possibility of the sun to set in east is 0.00 and the possibility for the sun to set in west is 1.00. The other possible degrees of likelihood range between these limits, 0.00 to 1.00, and are expressed in form of appropriate ratios. It is also worth mentioning here that if the probability of an event is higher, then there are more chances that the event will occur. For example, predicting whether it will be hot the next day will have more chance to occur if on the present day the temperature might have been high enough. Similarly, if the teacher has fallen sick, then it is more likely that he will not be coming to school on the next day. 14.2.1 Concepts related to probability. Probability is a statistical concept which can be measured and analyzed. Due to its much scientific applications, there are certain related concepts which you need to know. These concepts are 1. Sample space, events and power set, the collection or set of all possible results or outcome of an experiment or event is known as sample space. For example, in a die the all possible results to come when it is rolled ranges between 1 to 6, 1, 2, 3, 4, 5, 6 are the number of dots assigned at each respective face of the dice. So the sample space for the outcome of die ranges from 1 to 6. The subset of the sample space, which is a specified collection of possibilities from the overall possibilities, is called power set. If we consider that a collection of possible results can be all even numbers, 2, 4, 6, of the die, the subset, 2, 4, 6, is an element of the power set of the sample space of dice rolls. These collections are called events. In this case, 2, 4, 6 is the event that the die falls on some even number. If the results that actually occur fall in a given event, the event is said to have occurred. After considering all different collections of possible results of a sample space, a power set is formed. 2. Mutually exclusive disjoint events. Mutually exclusive event refers to incompatibility. Two events are said to be mutually exclusive if both cannot occur simultaneously in a single trial. In such circumstances, the occurrence of one event prevents the occurrence of other event. For example, when a single coin is tossed, there is a chance of either head, H, to appear or tail, T, to appear in a single trial, but both cannot be up at the same time, then both H and T are called mutually exclusive events. Hence, if H and T are mutually exclusive events, then probability, HT, equals 0. 3. Exhaustive collective events. An event is said to be exhaustive when its totality includes all possible outcomes of a random experiment. Meaning thereby, that out of a set of events, at least one event occurs in each trial. For example, if you throw a die, the outcomes will range in between 1, 2, 3, 4, 5 and 6. You cannot get 7 because it is not there in the die at all. Therefore the outcomes 1, 2, 3, 4, 5, and 6 are collectively exhaustive, because they constitute the possible entire range of probable outcomes. 4. Independent and dependent events. Two or more events are said to be independent events if the outcome of one event has no effect or is not affected by the outcome of the other event. For example, the results of tossing a coin will not be affected by the outcome of throwing a die. While dependent events are those events in which either occurrence or non-occurrence of one event in any trial affects the probability of other event in other trials. For example, we have 5 apples and 5 oranges in a basket. We take out one of the fruits, which could be apple or orange. If it was apple, then there are 4 apples and 5 oranges in the bag. Thus, the probability of the next fruit that we take from the basket being apple is 4/9. But if the first time the fruit was orange, then the probability would be 5/9. 5. Equally likely events. Events are said to be equally likely events if each event has a fair enough chance to occur approximately the same number of times. Thus, none of the event is more likely to occur more often than others. For example, if an unbiased coin is tossed, each face of the coin may be expected to be observed for the same number of times. 6. Complementary events. If two events are mutually exclusive and exhaustive, they both are said to complement each other. For example, if there are two events X and Y, then X is called the complementary event of Y and vice versa. Let us understand it by throwing a die. The occurrence of even numbers, 2, 4, 6, and odd numbers, 1, 3, 5, are complementary events. They are the two possible outcomes of an event, where they are the only two possible outcomes. 15.3 Concept, Nature and Properties of Normal Probability Distribution. A continuous probability distribution for a variable is called as normal probability distribution or simply normal distribution. It is also known as Gaussian, Gauss or Laplace, Gauss distribution. The normal distribution is determined by two parameters, mean and variance. The normal distributions are used to represent the real valued random variables whose distributions are unknown. They are used very frequently in the areas of natural sciences and social sciences. When the normal distribution is represented in form of a graph, it is known as normal probability distribution curve or simply normal curve. A normal curve is a bell-shaped curve, bilaterally symmetrical and is continuous frequency distribution curve. Such a curve is formed as a result of plotting frequencies of scores of a continuous variable in a large sample. The curve is known as normal probability distribution curve because its y-ordinates provides relative frequencies or the probabilities instead of the observed frequencies. A continuous random variable can be said to be normally distributed if the histogram of its relative frequency has shape of a normal curve, as represented in the below figure 14.1. 14.1. Normal curve. It is most important to understand the characteristics of frequency distribution of normal probability curve, NPC, in the fields of mental measurement and experimental psychology. 14.3.1 Importance of normal distribution. As discussed earlier, the normal distribution plays a very significant role in the fields of natural science and other social sciences. Some of the relevance of the normal distribution are described below. The normal distribution is a continuous distribution and plays significant role in statistical theory and inference. The normal distribution has various mathematical properties which makes it convenient to express the frequency distribution in simplest form. It is a useful method of sampling distribution. Many of the variables in behavioral sciences like weight, height, achievement, intelligence have distributions approximately like the normal curve. Normal distribution is a necessary component for many of the inferential statistics like z-test, t-test and f-test. 14.3.2 Properties of normal distribution. As discussed earlier, the representation of normal distribution of random variable in graphic form is known as normal probability curve, NPC. The following are the properties of the normal curve. It is a bell-shaped curve which is bilaterally symmetrical and has continuous frequency distribution curve. It is a continuous probability distribution for a random variable. It has two halves, right and left, and the value of mean, median and mode are equal. Mean equals median equals mode. That is, they coincide at same point at the middle of the curve. The normal curve is asymptotic, that is, it approaches but never touches the x-axis, as it moves farther from mean. The mean lies in the middle of the curve and divides the curve into two equal halves. The total area of the normal curve is within z plus or minus 3 sigma below and above the mean. The area of unit under the normal curve is said to be equal to 1, n equals 1, standard deviation is 1, sigma equals 1, variance is 1, sigma squared equals 1, and mean is 0, micro equals 0. At the points where the curve changes from curving upward to curving downward are called inflection points. The z-scores are the standard scores in NPC. Towards the right from the mean are positive and towards the left from the mean are negative. About 68% of the curve area falls within the limit of plus or minus 1 standard deviation, plus or minus 1 sigma, unit from the mean. About 95% of the curve area falls within the limit of plus or minus 2 standard deviations, plus or minus 2 sigma, unit from the mean, and about 99.7% of the curve area falls within the limit of plus or minus 3 standard deviations, plus or minus 3 sigma, unit from the mean. Refer to figure 14.2. The normal distribution is free from skewness, that is, its coefficient of skewness amounts to 0. The fractional areas in between any two given z-scores is identical in both halves of the normal curve. For example, the fractional area between the z-scores of plus 1 is identical to the z-scores of minus 1. Further, the height of the ordinates at a particular z-score in both the halves of the normal curve is same. For example, the height of an ordinate at plus 1z is equal to the height of an ordinate at minus 1z. Normal probability. 14.2. Normal probability curve, NPC. Check your Prograd score or z-score as a transformed score which shows the number of standard deviation units by which the value of observation, the raw score, is above or below the mean. The standard score helps in determining the probability of a score in the normal distribution. It also helps in comparing scores from different normal distributions. Score. The standard score is a score that informs about the value and also where the value lies in the distribution. Typically, for example, if the value is 5 standard deviations above the mean, then it refers to 5 times the average distance above the mean. It is a transformed score of a raw score. A raw score or sample value is the unchanged score or the direct result of measurement. A raw score, x, or sample value cannot give any information of its position within a distribution. Therefore, these raw scores are transformed into z-scores to know the location of the original scores in the distribution. The z-scores are also used to standardize an entire distribution. These scores, z, help compare the results of a test with the normal population. Results from tests or surveys have thousands of possible results in units. These results might not be meaningful without getting transformed. For example, if a result shows that height of a particular person is 6.5 feet, such findings can only be meaningful if it is compared to the average height. In such a case, the z-score can provide an idea about where the height of that person is in comparison to the average height of the population. 14.4.2 Properties of z-score. Following are some of the properties of the standard z-score. The mean of the z-scores is always 0. It is also important to note that the standard deviation of the z-scores is always 1. Further, the graph of the z-score distribution always has the same shape as the original distribution of sample values. The z-scores above the value of 0 represent sample values above the mean, while z-scores below the value of 0 represent sample values below the mean. The shape of the distribution of the z-score will be similar or identical to the original distribution of the raw scores. Thus, if the original distribution is normal, then the distribution of the z-score will also be normal. Therefore, converting any data to z-score does not normalize the distribution of that data. 14.4.3 Uses of z-score. Z-scores are useful in the following ways. It helps in identifying the position of observations in a population. Distribution. As mentioned earlier, the z-scores helps in determining the position, distance of a value or an observation from the mean in the units of standard deviations. Further, if the distribution of the scores is like the normal distribution, then we are able to estimate the proportion of the population falling above or below a particular value. Z-score has important implication in the studies related to diet and nutrition of children. It helps in estimating the values of height, weight and age of children with reference to nutrition. It is used for standardizing the raw data. It helps in standardizing or converting the data to enable standard measurements. For example, if you wish to compare your scores on one test with the scores achieved in another test, comparison on the basis of raw score is not possible. In such a situation, comparisons across tests can only be done when you standardize both sets of test scores. It helps in comparing scores that are from different normal distributions. As mentioned in the previous example, z-scores help in comparing scores from different normal distribution. Thus, z-scores can help in comparing the IQ scores received from two different tests. 14.4.4 Computation of Z-score. As mentioned earlier, z-score refers to the distance of the sample value from the mean in the standard deviations. Z-score can be computed for each value of the sample. The following formula is used to compute z-score of a sample value. Z equals xm, SD or Z equals xm, sigma. Where x equals a particular raw score, m equals sample mean, SD or sigma equals standard deviation. To illustrate, suppose the following are the marks obtained by students in mathematics. The marks obtained are expressed here in terms of raw scores. The mean, SD and z-scores can be then calculated accordingly. Students' raw scores, x, xmza 50 to 15 minus 1.24 b 60 to 5 minus 0.41 c 66 1 0.08 d 75 0.41 e 81 5 1.24. N equals 5 sum 326 mean 65 SD 12.04. The above illustration shows the z-scores of the marks obtained by each student, A, B, C, D and E. In the above example, student A is 1.24 standard deviations, or 1.24 standard deviation units below the mean. Similarly, the student E is 1.24 units above the mean. The standard deviation is used as unit of measurement in standard scores. The standard score helps in normalizing or statistical methods too. 246. Collapsing the data to a common standard based on how many standard deviations values lie from the mean. The variation of z-scores range from -3 standard deviations, which would fall to the far left of the normal distribution curve, up to +3 standard deviations, which would fall to the far right of the normal distribution curve. Further, we need to know the values of the micro, mean, and also the sigma, standard deviation, of the population. Thus, if we want to compute z-score for x equals 70, m equals 65 and SD equals 12.04, we will use the formula z equals xm, SD equals 70 to 65, 12.04. Equals 5, 12.04 equals 0.42. Thus, the Z-score is obtained as 0.42. Check your progressions from normality, skewness and kurtosis. Many times, the frequency curve may be more peaked or flatter than the normal probability distribution curve. In such cases, the distribution is said to have diverged from normality. Basically, these divergences are of two types, kurtosis and skewness. Kurtosis is a measure of tailedness of the probability distribution of a random variable. In other words, it is a measure whether a data is heavy-tailed or light-tailed in relation to normal distribution. On the other hand, skewness is a measure of asymmetry of the probability distribution of a random variable about its mean. Let us discuss both the divergences one by one. 14.5.1 Kurtosis deals with the tails of distribution curve and not its peak. It does not refer to the height of the curve. Kurtosis can be quantified in various ways for a particular distribution. The kurtosis of any variable in normal distribution is 3. This value is used for comparison with respect to the other types of kurtosis. The kurtosis is classified as follows, refer to figure 14.3. Normal probability. Distribution. 247. 1. Leptokurtic. In a leptokurtic distribution, the frequency curve is narrower than the NPC and the area of the curve shifts towards the center and has longer tails at both the ends. Usually they are referred to as positive kurtosis, in which the value of distribution has heavier tails than the normal distribution, refer to figure 14.3. 2. Mesokurtosis. A mesokurtic curve is not too flat or not too peaked and in a way resembles normal curve, Mongol, 2002. 3. Platykurtosis. Platykurtic curve refers to the distribution having fewer and less extreme outliers than does the normal distribution. Usually they are referred to as negative kurtosis, in which the value of distribution has lesser or fewer tails or outliers than the normal distribution. The curve in platykurtic is flatter when compared with normal curve, refer to figure 14.3. Fig. 14.3. 3 types of kurtosis. Kurtosis can be computed with the help of the Q equals Q, P90 P10, where Q equals kurtosis, Q equals quartile deviation, P90 equals 90th percentile, P10 equals 10th percentile. Mesokurtic. Platykurtic. Leptokurtic. Statistical methods 2. 248. When kurtosis value is computed with the help of the above formula, the value for normal curve is obtained as 0.263. If the value obtained is below 0.263, then the curve can be termed as leptokurtic, and if the value is above 0.263, then the curve can be termed as platykurtic, Mongol, 2002. 14.5.2 Skewness. As informed to you earlier that in NPC, the mean, median and mode coincide together, fall at same point, and have equal values. In a skewed distribution, the mean, median and mode fall at different points in the distribution, and the center of gravity is shifted to one side. So, the skewness determines the lack of symmetry in the curve, and since normal probability is a symmetrical curve, it has zero skewness. Skewness can be measured in terms of Pearson's measure and percentiles. Depending upon the distribution of scores, skewness can be classified into 2 types as mentioned below. 1. Positive skewness. A distribution curve is said to be positively skewed when the distribution of scores are more at the left end, refer to figure 14.4. In a positively skewed distribution, more individuals option scores that are less than the mean. Fig. 14.4. Positive skewness. 2. Negative skewness. On the other hand, if the distribution of the scores fall more towards the right side, the distribution is said to be negatively skewed, refer to figure 14.5. The median here is greater than the mean, and that is why the mean lies to the left of the median. Here, more individuals obtain scores that are higher than the mean. Mode. Median, mean. Normal probability. Distribution. 249. Fig. 14.5. Negative skewness. Skewness can be computed with the help of the following formula. Sk equals 3 mmd. SD, where Sk equals skewness, M equals mean, MD equals median, SD equals standard deviation. There is another formula to compute skewness that is used when the information about percentiles is available. US sum up. To sum up, in the present unit we discussed about the concept of probability. Probability refers to chance or likelihood. For example, if you say that, it will probably be hot tomorrow, or probably the teacher might not come tomorrow, the sentences reveal that there are chances for the events to occur tomorrow, but there is no certainty. Some of the significant concepts related to probability were also discussed, like sample space, events and power set, mutually exclusive, disjoint events, exhaustive, collective events, independent events, equality, likely events and complementary events were also discussed. Further, the concept and nature of normal probability distribution were also highlighted with the help of a figure showing normal probability curve. A normal curve is a bell-shaped curve, bilaterally symmetrical and continuous frequency distribution curve. Such a curve is formed as a result of plotting frequencies of scores of a continuous variable in a large sample. The curve is known as normal probability distribution curve because its y-ordinates provides relative frequencies or the probabilities instead of the observed frequencies. Standard score or Z-score was also discussed in detail in the discussion covered properties, uses and computation of Z-score. Lastly, the unit explained divergence from normality, where kurtosis and skewness, along with their types, were discussed with help of figure. 14.8 Keywords events, a set of outcomes of an experiment. It is the subset of the sample space. Kurtosis. Kurtosis is a measure of tailedness of the probability distribution of a random variable. In other words, it is a measure whether a data is heavy-tailed or light-tailed in relation to normal distribution. Normal probability curve. A normal curve is a bell-shaped curve, bilaterally symmetrical and continuous frequency distribution curve. Statistical methods 2. 252. Normal probability distribution. A continuous probability distribution for a variable is called as normal probability distribution or simply normal distribution. It is also known as Gaussian, Gauss or Laplace, Gauss distribution. Probability. In statistics, the term probability refers to the expected frequency, chance, of occurrence of an event among all possible similar events. Skewness. Skewness is a measure of asymmetry of the probability distribution of a random variable about its mean. Standard score. Standard score or Z-score is a transformed score which shows the number of standard deviation units by which the value of observation, the raw score, is above or below the mean. 4.
इसी के साथ ही हमारा ब्लॉक 4 जो कि यूनिट 12 से स्टार्ट हुआ था और यूनिट 14 पे एंड होता है, ये ख़त्म हो रहा है। इसमें जो कुछ भी प्रॉब्लम्स थे थियोरेटिकल के अलावा, जो कुछ भी प्रॉब्लम्स थे वो मैंने आपको ही दे दिए हैं। आपको खुद एक टेक्स्ट बुक नोटबुक लेके इनको सॉल्व करना है ताकि आपको डिटेल में ये पता लग पाए। और ये भी मैंने प्लान किया है कि एक मैं इंडिविजुअल प्रॉब्लम सॉल्व करते हुए वीडियो बनाऊं।